You might have observed that when a spring is compressed from its natural length and then it is released from this particular position, compressed position, it automatically takes this block towards right. It is able to create a force on the block and is able to take the block to the right, isn't it? Similarly, if the same spring is stretched from its natural length and then from this stretched position, if we release the spring and the block system, we see that the block is automatically able to move towards left and gain energy, gain kinetic energy in the process of doing that. So, if we try and understand and we try to ponder over this as to what is happening, why is the spring able to create a motion in the block, how is the spring able to exert a force on the block, other than the concept of force, we can understand this from the concept of energy as well. We say that when a spring is compressed or stretched, it has a certain amount of energy stored within it, which is purely due to the state in which it is. The state which is a compressed state or a stretched state other than its natural state in which the spring tries to be. If it is in a state different from that, we say that there is a energy stored within the spring, and it is this energy that works on the block as we release this compressed or stretched spring block system. This energy stored in the spring is called the spring potential energy. Potential energy, as the term suggests, is the energy that comes out of a body which has a certain potential to do work because of its state, the state in which it is, the configuration in which it is. So, today's topic is potential energy, a very important topic. We'll understand this with respect to two very important forces. One is the spring force and the other is the gravitational force, both of which are special type of forces. We shall see what speciality do they have. So, in order to understand this, I will take one more example here before we start with it. On the same lines as we have discussed for a spring, do we all know that when this ball, which was initially on the ground, is taken to a certain height, let us call this height as h, this is taken to a height h, and from that height if this ball is released, we know that it comes down naturally. How does it come down? If we try to explain it on the basis of force, we can say that gravity pulls it down and hence it undergoes an acceleration. It comes down and as it comes down, it will gain speed and hence kinetic energy. But how do we express this in terms of the energy concept? How do we explain why the ball comes down depending upon the energy? We say that at a height h, this ball has something that we can call as the gravitational potential energy, the potential energy associated with gravitational force, due to which when you release it from a certain height, it automatically uses this energy to come down and gain speed in the process of that. Okay. So, potential energy then we say is the energy that is possessed by a body or a system of bodies due to their configuration or position. Body being in a certain position can possess a potential energy, or if a system is in a certain configuration. For example, in this first example, there was a spring block system whose configuration was changed from its natural length configuration, right, and it is because of this change in configuration the spring block system gained the potential energy, right. So, this is how we give the definition of potential energy. The basic definition says that it is the energy possessed by a body due to its position and or configuration. Now, before we understand potential energy a little more in detail or the mathematical definition, we have to understand the concept of what we call as conservative and non-conservative forces. So, let us understand that first. So, our next topic would be conservative and non-conservative forces. Now, what are these? To understand the concept of conservative and non-conservative forces, once again let us take up an example. Okay. There is this ball which was initially on the ground, and by some force acting on the ball, this ball goes up to a height of h from the ground. It is taken to a height h actually by applying an external force. Okay. Now, in the process of this ball going up from, let us say, the position A to the position B, can we find out the work that gravity will do on this ball? If we assume that the ball has a mass m, can we say that gravitational force of mg is acting on the ball at all the times, and in the process of moving the ball from the ground to a height h, the work done by gravity will be the force of gravity mg times the displacement of the ball, that is h, times cos of the angle between the force of gravity and the displacement h, which is 180 degrees. Gravitational force is downward, h the displacement is upward. So, what do we get the work done by gravity here? It is mgh, right, in the process of taking the ball from A to B, right. Now, as the ball goes up, work done by gravity is minus mgh. Let us also find out the work done by the same gravitational force as the ball comes back from B to A. What will this be? As the ball now comes back from the point B to the point A, can we say the same force of gravity mg undergoes, under the effect of this mg, the ball undergoes the same displacement h, but this time the displacement h will be downward, no? So, it is in the same direction as the gravitational force. So, the cos term will be cos 0, which is 1. So, the work done by gravity this time will be mgh plus mgh. Now, there is something that we define as the work done in a closed path or for a round trip. Work done for a round trip means work done by a force when a body starts from one position and after undergoing a certain displacement comes back to the same position, so that its net displacement is 0. Can we say that in this particular figure, work done for the round trip will be the work done from A to B plus the work done from B to A? We just need to add the two works. By gravity we are trying to find out the work done for a round trip. Can we say in this case this will come out to be minus mgh plus mgh, which is nothing but 0. So, this is an important characteristic of conservative forces. In fact, sometimes conservative forces are defined the same way. Conservative forces are called to be those forces for which the work done over a closed trip, closed loop is 0 for conservative forces. Okay? Gravitational force is one such force. Okay. There is another force like that, which is the spring force. Let us check the same thing for spring force also. Let us say there is a spring which is attached to a block of mass m, and by applying an external force, this block is taken from the position x is equal to 0 to a final position, which is, let us say, x is equal to x naught, right. Throughout this motion there was a force acting on the block. And do we understand that as the block starts moving towards right, the spring will start exerting a backward restoring force, which we call as the spring force kx, right. And we also know that in the process of movement of the block from initial position to the final position, the work done by the spring in motion from the point A to the point B will be minus half kx x naught squared. This we have studied in the previous lecture. We have seen how to find out the work done due to a spring, where k is the spring constant of the spring and the spring undergoes a total extension or compression of x naught. This is what we get as the expression for work done by the spring there, right. So, from A to B, when the spring, when the block moves, the work done by the spring is minus half kx naught squared, right. Now, after taking the block to the position B, if we now bring it back to the position A, as it comes back, do we understand that the spring force will still be towards left? Because the spring is in a stretched state, it will always try to pull the block towards itself, back to the natural length. So, can we say this work done by the same spring, now when the block moves from B to A, will be half kx naught squared only, but with a plus sign now, plus half kx naught squared. This we can understand because now kx, the spring force, as well as the displacement x naught will be in the same direction. So, work done by the spring has to be positive, and since the expression comes out to be the same, half kx squared, which we have obtained by the way by integrating kx dx. If you remember, this is the process of finding out the work done by a spring. This was from x is equal to 0 to x naught, which gave us minus half kx squared, because the spring force kx and the displacement were in the opposite direction. This was from A to B, but from B to A, our limits of integration will be from x naught to 0 and the force will be kx dx. So, this will come out to be plus half kx x naught squared as the spring comes back to its natural length. So, now understand that when we once again try to find out the work done for the closed trip from A to B and then back to A, this will be nothing but the work done from A to B plus the work done from B to A, which will once again come out to be 0. This makes us understand that a spring force is also a conservative force. Mathematically, this is the definition for a conservative force. Otherwise, in physics, in terms of physical significance, if we try to understand the behavior of conservative forces, as the name suggests, we say that conservative forces are the ones that conserve the energy of the system as they work upon them. So, here we see that as this ball was made to move from the ground to a height h, gravity does a work on it, a negative work on it, right. So because of that, what happens is the ball which moves up will gain a certain energy as it reaches this height h. It is that energy that it gains because of the gravity doing work on it, which we shall be defining as potential energy. It will come in a while, we shall understand it there. So, we say that whenever a conservative force does work on a system, it does not dissipate the energy of the system, it only changes the energy of the system from one form to another. Okay? So, same thing in the spring also. In the spring case, when the block moves from the position A to the position B, it might lose some kinetic energy. Maybe the block was given some initial kinetic energy due to which it started moving towards right, but as it moves towards right and as the spring does work on it, by the time it reaches the position B, it will gain a certain amount of potential energy, which will then help it go back and gain once again the kinetic energy. Okay. So, this is what makes us understand about conservative forces. The conservative forces are the ones that will do net zero work over a closed path. Now, on the other hand, what are non-conservative forces? Once again, can we say non-conservative forces should be the ones that do not conserve the energy of a system, they rather dissipate the energy of a system. How does this happen? Let us take the example of a non-conservative force. Friction is a non-conservative force. So, just to take an example, let us say we have a block of mass m, which is made to move towards right under the effect of an external force, and in the process of that, let us say there is a frictional force acting on the block towards left. Now, do we understand that as the block moves from the position A, let us say to a new position B, the work done by friction will be the frictional force times the displacement from A to B, let us call it S, F into S into cos of the angle between the force of friction into the displacement, which is 180 degrees. Friction is towards left, displacement is towards right. It will be minus of F into S, that is the work done by friction. Friction can take any value here, maybe if you know the value of mu, friction will be mu n, right. So, we understand that we can easily find out the work done by friction as it moves from A to B. Now, what will happen when the same block moves back from B to A? How do we find out the work done by friction then? Do we understand that when the block starts moving back from B to A, this time friction will change its direction. Friction will now start acting towards right. Friction will be acting like this now. And as the block moves towards left this time, the same displacement, can we say the work done by friction will still be negative of F dot F into S? Because friction is still opposing the displacement. And in this case then, the work done over a closed loop, closed strip from A to B and then back to A will be nothing but minus of Fs in plus minus of Fs, which is not 0 this time, it is minus 2 times Fs rather, right. So, here we see that the work done by friction is not 0 over a closed path. So, once we have understood the basic definition and the physical significance, we now move back to the potential energy. Now that we have understood that gravitational force and spring force are two conservative forces, and frictional force, and understand that all the other forces which are dissipative in nature, for example, air drag, air friction, viscous force due to a liquid, all such forces, because they are resistive in nature, they are kind of drag forces, they will all be dissipative forces in nature, and they will not be able to keep the energy of a system conserved, due to which they are non-conservative. Now, when we go back to potential energy, there is an important statement that we make here. We say that the potential energy can only be defined for conservative forces. We cannot define a potential energy for non-conservative forces, a very, very important definition. So, it is only for forces like gravitational force or spring force that we can define potential energy. We cannot define potential energy for friction. Okay? And now, how do we define potential energy? We say that it is not the potential energy as such that can be defined. What we define as the change in potential energy. Change in potential energy, which we can write in short as PE, or another letter that we use to denote potential energy is capital U. Change in potential energy is defined as, now we come to the mathematical definition of potential energy. We say that change in potential energy, delta U or delta PE, is equal to the negative of the work done by the conservative force acting on the system under study. So, we say that in case we have a system which when moves or some change happens to it, there is a conservative force involved in the system, there is a conservative force doing work on the system. In that case, if we can find out the negative of the work done by the conservative force as the system moves, it is from there that we can define the change in the potential energy of the system, and this is the most important, the most basic definition of potential energy. Okay. Just to give you an example, maybe we shall work with both the conservative forces that we have discussed just now. The one is the gravitational force and the other is the spring force. So, let us take their examples one by one. So, let us say we have got a ball which is initially held on the ground, and a force acts on the ball and it reaches till a height h under the effect of that force. To a height h it goes. Okay. Now, do we understand that at all the times the weight of the ball was mg in the downward direction, right? And we can easily find out the work that this force will do on the ball as it reaches to a height h. What will be the work done by gravity as the ball moves from the position A to the position B? Can we say that the work done by gravity, work done by mg, will be mg into h into cos of 180 once again, because the force of gravity is acting downward whereas the displacement is upward, and this work done comes out to be minus mgh, right? Now, according to the definition, this minus mgh, which is the work done by gravity, we can use here to find out the change in potential energy of this ball from the position A to the position B. How do we write it? We write it as change in the potential energy, which will be the final potential energy at the position B minus the initial potential energy at the position A, should be equal to negative of the work done by gravity. Let us substitute that here. We get potential energy at B minus potential energy at A is equal to negative of minus mgh. Minus mgh is the work done by gravity, isn't it so? Which then becomes mgh itself. Minus signs cancel out. And from here we write potential energy at B is equal to potential energy at A plus mgh. Now, this expression is a very important expression to understand about potential energy. This expression is telling you that if you want to find out the potential energy at the point B, what you first need to know is the potential energy at the point A. Only then you can find out the potential energy at the point B, and this is one of the most basic aspects of potential energy, and that is why we say that we can define only change in potential energy. Delta PE is what we can define. We cannot in the first place define the potential energy at any particular position. because in order to define the potential energy at a point, you first need to define the potential energy at the base level, which we are considering as the point A. So, here we say that if we know the potential energy at A, or if we are able to first give some value to the potential energy at A, only then we can write the potential energy at the point B. So, what we generally do here in this case is, we take the potential energy at the ground level, which is our position A right now, to be 0. If we do that, potential energy at A, if we take it to be 0, can we say we can easily find out the potential energy at B, right? So, from here can we say we will get potential energy at B is equal to 0 plus mgh, and that will be mgh itself. So, it is this potential energy at B which you call as mgh, which is under the assumption or under the reference that the potential energy at the point A is 0. At the ground, if the potential energy is 0, then at a height h the potential energy will be mgh. Okay, you all need to understand this very, very carefully. This is one of the most basic things about potential energy. Okay, you could have taken any other value for potential energy at the point A, and then corresponding to that the potential energy at B will change. How will it change? From the same equation that we have obtained here. The difference of the two potential energies will remain the same. So, whatever value of potential energy you give to the point A, corresponding to that you will get the potential energy at the point B. Okay, I hope this concept is clear. Let us try using this into the spring block system as well. Okay. So, let us say we now have a spring which is initially in its natural length, and it is connected to a block of mass m, let us say, and by applying an external force F, this block was taken from the initial position, which was x is equal to 0, which is corresponding to the spring being in its natural length, to a final position which is x is equal to x naught, where we understand that the spring gets stretched by a distance x naught, right. So, can we say here in this case the work done by the spring, as we have already seen also, will be minus half k x naught squared, and corresponding to that, now if I try to write the expression for change in potential energy as negative of the work done by the conservative force, which in our case is the spring force. The spring force is the conservative force now. So, it will be negative of the work done by the spring force, which will be negative of minus half k x naught squared, which comes out to be half k x naught squared. And this expression tells you that the potential energy at the, let us call the initial point as the point A, the final point as B, potential energy at B minus potential energy at A, that is the change in potential energy, right. That is coming out to be half k x naught squared, which means that if you want to find out the potential energy at B, all you need to do is first take the potential energy at A and then add to it half k x naught squared, right. The same way as we have obtained for the above case, the previous case. So, here also we need to first define the potential energy at the position A of the spring block system, which is this position where the spring is in its natural length. By convention, we take the potential energy of the spring at its natural length to be 0. And then we can say that the potential energy at the position B, where the spring is stretched by a distance x naught, comes out to be half k x naught squared from there. So, understand that this relation once again is coming once we have defined the reference position, the position where we take the potential energy of the spring block system to be 0, right. So, in these two cases we have defined two types of potential energies. In the case of gravitational force acting on a system, the potential energy that we get here is the gravitational potential energy. This PE is called the gravitational potential energy. Whereas, in case of a spring block system, the potential energy that gets stored into the system is called the spring potential energy, or also the elastic potential energy. Okay. One more thing we can observe from here is that when this ball was taken from the position A to the position B, there would have some force acted on the ball, no? For sure there would be a force that will take the ball from position A to position B. Now, other than mg, if there is another force acting on the ball, that will also do some work on the ball in the process of taking it from A to B. In fact, if we put a condition that this force F that acted on the ball took the ball upward slowly and steadily. When we say slowly and steadily, this means that the ball was taken up without any acceleration, right, and without any appreciable velocity. So, the ball moved slowly with zero acceleration, and the condition for that is that the external force F that acted on the ball at any point in time will balance its weight completely. Only then the net force on the ball will be 0 and its net acceleration will be 0. If that is true, can we say that this means that the force F, which is just equal and opposite to mg, of course they are equal and opposite, right? Force F is acting upward whereas mg is acting downward. Can we say that the work done by this force F will be just negative of the work done by gravity? Because both the forces are equal and opposite, and we are discussing a certain displacement. So, as we measured the work done by gravity when the ball moved a height h up as minus mgh, can we say that the work done by the force F in the same displacement from A to B will be plus mgh? You can look at it on your own, because this F by magnitude now it is the same as mg. So, if there is a force of mg acting upward and the ball undergoes a displacement of h upward, can we say the work done by the force F will be the force into the displacement, simply mg into h? And in that case, can we say the definition that we have given for change in potential energy, delta U is a negative of the work done by the conservative force, can we modify this definition and say that it can also be plus the work done by the external force which creates the change in the configuration of the system? Because this external force at any point in time is equal and opposite to the conservative force. So, it will do equal and opposite work in changing the configuration of the system. So, this is an important point to understand, that we can define change in potential energy in terms of two distinct forces. One is the conservative force that is acting on the system, and the other is the external force which is acting on the system, which is making the system change its configuration in terms of both. So, either you use the first definition, change in potential energy is negative of the work done by the conservative force, or you say that change in potential energy is positive of the work done by the external force. Let us look at the same thing here in the spring force also. Do we understand that when this block was taken from x is equal to 0 to x is equal to x naught, there would have been an external force F acting on the block at all the times, right? And if we assume that this block was taken to the right with no acceleration and with almost 0 speed, slowly and steadily, v is almost 0 and acceleration is 0. As soon as we say that acceleration of the block is 0, that means the net force on the block is 0. Now, we understand that when the block is any intermediate point anywhere where the displacement of the block is x and the spring is also stretched by x, the spring force that will come and act on the block will be kx in the backward direction, leftward direction. Whereas, if you want the block to move forward with 0 acceleration, the external force F should balance the spring force kx at all the times, right. So, since the external force F is always equal to the spring force kx, just that it is in the opposite direction, can we say that the work done by this external force F at any point in time will be just the negative of the work done by the spring force? And hence, when we say the change in potential energy is negative of the work done by the spring force, it can also be called to be the positive of the work done by the external force F, right. So, in that sense, we understand that delta U can also be defined in terms of the external force. This definition is useful sometimes while doing questions. It is easy to work with the conservative force. Some other times it might be easy to work with the external force and try to find out the work done and hence the change in potential energy. Okay, so it depends upon the system, but you should understand that both the definitions can be used interchangeably. Okay. So, the next thing that we can take up now is the law of conservation of energy. Law of conservation of energy. A very important law. We use it into questions directly, but as we shall be deriving it here, we shall see that there are some conditions attached with it, and only when those conditions are satisfied we can use the law. Okay. In fact, we shall be deriving this law from the work energy theorem that we have already studied in the previous lecture. The work energy theorem, which says that work done by all forces is equal to the change in the kinetic energy of the system. This is the theorem, right, that we studied in the last class. So, when we say work done by all forces, do we understand that all forces will include all types of forces acting on the system, which in general could be distinguished into two parts: work done by the conservative forces plus the work done by the non-conservative forces, right. This is how we can split all the forces into two parts. This should be equal to the change in the kinetic energy. So, this is our work energy theorem when we write it in terms of the types of forces that are acting and working on the system. Now, for the law of conservation of energy to be valid, right, we say that the work done by non-conservative forces, this term should go to 0. Okay. So, what do we mean by this? If work done by non-conservative forces is 0, what does that mean? That means that no force which is non-conservative in nature, like friction, air drag, viscous force, none of them are doing work on the system. Okay. They might act on the system, but they should not do work on the system. See, one thing is, if they are not at all acting, then anyway they can't do any work. But even if they are acting on the system but not doing any work, we say that even then the law of conservation of energy would be valid. Okay. There are cases that we shall be studying in the upcoming chapters. For example, the chapter on rotational mechanics, where we talk about bodies rolling over a ground, we shall see that in case of rolling motion, there is a force of friction that comes and acts on the bodies at the bottommost point, the point where the body is in contact with the ground, but that friction will not do any work there. And hence, even though friction is acting on the body, since the work done by it is 0, we will say that this expression for work done by non-conservative force will be still be 0, and we can still conserve the energy of the system. So, that is an important case for this particular expression to be becoming 0, even if there is a non-conservative force acting. So, the important thing here is that no work should be done by non-conservative forces. Okay, this should be very, very clear to all of you. So, if the work done by non-conservative forces is 0, this implies that only the conservative forces are doing work. The second term will become 0, and this should be equal to the change in kinetic energy, right. Now, from the above definition that we have given for potential energy, from there can we write the work done by conservative forces in terms of the change in their potential energy? We know from the above definition that change in potential energy is negative of the work done by the conservative forces, right. From this, can we write work done by conservative forces as negative of the change in potential energy and substitute this value over here? That gives us negative of change in potential energy is equal to the change in kinetic energy of the system, right. This is what this expression becomes. And from here, can we write this implies that the change in kinetic energy plus the change, by taking this term on the right hand side, plus the change in potential energy, this must be 0. And this is the law, that this is the expression that we are looking for. This expression is, if we combine the kinetic and the potential energy together, what we get is mechanical energy. So, this means that the change in mechanical energy is 0. Like change in mechanical energy 0 means the mechanical energy of the system remains constant, which is nothing but the law of conservation of energy. What is the law? It says that if no non-conservative forces are doing work on the system, then the total mechanical energy of the system remains constant. What is the total mechanical energy? Mechanical energy, we all know now, it contains two types of energies. One is the kinetic energy and the other is the potential energy. So, when we say that the mechanical energy of a system remains constant, it does not change. We mean that the mechanical energy of the system initially is equal to the mechanical energy of the system finally. If a system undergoes some change in its configuration or something, which also means that the initial kinetic plus potential energy is equal to the final kinetic plus potential energy of the system. This is our law of conservation of energy. Okay, so this law, as you can all see, is coming from the work energy theorem. What does that imply? That implies that work energy theorem is even more general theorem. As I told you when we were discussing work energy theorem, that work energy theorem is more general than the law of conservation of energy, because work energy theorem works with non-conservative forces also. Even when non-conservative forces are doing work, you can still use the work energy theorem there, right? But for the law of conservation of energy to be used, work done by non-conservative forces must come out to be 0, right? So, in that sense we say that work energy theorem is a more general theorem. Fine. So, what is the statement for law of conservation of energy then? Let us just discuss it once again. According to the law of conservation of energy, the total energy of a system remains conserved if there are no non-conservative forces doing work on the system. They might act on the system, but they should not be doing any work. Okay, this is the law, a very important law. We directly use it into questions and see how it it is able to give us quantities that are unknown. So, quickly let us take up a couple of examples to understand how we use this law into questions. A very simple question may be, there is a ball which is thrown up from the ground level, the position A, with an initial speed u, and we are supposed to find out the maximum height h to which the ball will go. We are not supposed to use the force method here. We are not going to discuss forces acting on the ball and using equations of motion. We have to directly work with the energy concept. Let's see how we do that. Do we understand that as the ball reaches to the topmost point, its velocity just becomes 0? And as the ball moves from position A to B, the only force that acts on the ball is its gravitational force, the gravitational force acting on the ball, which we now know is a conservative force. And if it is a conservative force, I can conserve the total energy of the ball between the points A and B. So, we use the law of conservation of energy between the points A and the points B. So, we say that the kinetic plus the potential energy at A should be equal to the kinetic plus the potential energy at B. What is the kinetic energy at A? The kinetic energy at A is half mu squared plus the potential energy at A. Now, we need to take a reference over here. We need to fix up where we take the potential energy to be 0. So, let us take the potential energy at the ground level to be 0. Potential energy at A is 0. So, this becomes 0 here. This should be equal to the kinetic energy at the position B. At the point B, we understand that because that is the highest point of the ball, there its velocity will become 0 for an instant. So, the kinetic energy at the point B will be 0. Plus the potential energy at the point B. Do we understand? Now we can write it as mgh. The gravitational potential energy of the ball at a height h from the ground is mgh if we have considered the potential energy at the ground to be 0, right? So, this is the expression that we get, and you see that you can directly solve this expression to whatever you want. If you want the value of h from here, you can write h is equal to u squared by 2g. Right, and that gives you directly the answer in one single equation. It gives you the height, right? Let's take another example. Example number 2 says there is a spring of spring constant k, let's say, which is initially in its natural length, and you just connect a block of mass m with it while keeping a support beneath. There is a support which makes sure that the spring does not open up. Right now x is 0. So, this is the level where the spring is in its natural length. Now, suddenly this support beneath the block is removed. As it is removed, do we all understand that because of the gravitational force, the block will start moving down? As it moves down, the spring will open up and will start exerting an upward force on the block. So, after undergoing a certain displacement, the block will reach a certain lowest position, from where it will then again start turning back, like moving upward. We are supposed to find out the lowest distance or the lowest position to which the block reaches, after which it will start moving up. So, to find out the lowest position, let's assume that this distance that the block travels in the downward direction is, let's say, x. And since this is the lowest position, we call the first position as position A, the second one as B. Let us assume that the potential energy at the point B of the block is 0. Because this is the lowest position, we can always assume it like that, though we can take the other way around also. So, potential energy at B if we consider to be 0, can we say that the potential energy at the point A then, which potential energy are we talking about here? We are talking about the gravitational potential energy. At the point B, the gravitational potential energy is 0. At the point A then, which is at a height x above the point B, can we say the gravitational potential energy will be mgx, right? Now, do we all understand that as the block moves from the position A to B, the spring also opens up, spring also does work, corresponding to which there will be a change in the spring potential energy as well. So, there are two forces acting on the block as it moves from A to B, the gravitational force and the spring force, both of which have their potential energies defined, right? Can we say that we can also write the expressions for spring potential energy at A and B? This is the gravitational potential energy, so I will denote it with the letter G, whereas the spring potential energy at A, PE at A due to the spring, can we say this will be 0? Because by definition, as I told you, the standard notation is that when the spring is in its natural length, we take its potential energy to be 0. Whereas when the spring opens up by a distance x at the position B, can we say the spring potential energy at B will be half k into x squared? Isn't it so? And now, one more thing, what about the kinetic energies? At the point A, the block was at rest and it was released from rest. Suddenly, when the support was removed beneath it, the block started to move from rest. So, can we say the kinetic energy at the position A is 0? Because its velocity is 0 there. And what about the point B? Point B is the point where the block, after having travelled a certain distance, once again comes at rest, because after this block is going to move up again. It is not going to go further down. So, can we say at the point B also the velocity of the block is 0, which means that the kinetic energy at B is also 0, right? So, having discussed all the energies that the block have at the positions A and B, can we use the law of conservation of energy between the points A and B and say that the mechanical energy at A should be equal to the mechanical energy at B, which means that the kinetic plus the potential energy at A, which will now be the sum of all these three energies, 0 plus mgx plus 0. So, that is mgx, only gravitational potential energy is there at the point A, is equal to the mechanical energy at the point B, which is now the sum of these three energies. At the point B, the only energy that the system has is the spring potential energy due to a stretch of x in the spring, which is half k x squared. There is no gravitational potential energy, there is no kinetic energy, right? And it is this equation which will now directly give you the value for x. See that one x cancels out, and from here you get x is equal to 2 mg by k. Okay. There is one important aspect that needs to be understood here for this particular question. Understand that neither of the positions A and B are equilibrium positions. At both the positions, the block will have a certain acceleration. At the point A, the acceleration will be downward because the spring force is 0 there and the mg force is acting downward, right? Whereas at the position B, the block will have a net acceleration upward, because at the point B, the block will start moving up back again. So, that means the spring force then overtakes the gravitational force and the block starts moving up. So, at the position A, the net force is downward, at the position B, the net force is upward. Do we understand that the equilibrium position for the spring block system will lie somewhere in the middle of the two positions? In fact, from our previous chapter, laws of motion, we know that when a spring block system is hung like this, the equilibrium state x naught comes out to be mg by k. How does this come? We say that the spring force kx naught balances the weight of the block. So, x naught comes out to be mg by k, and if you just look at this carefully, this x that we have obtained is just the double of this x naught. So, what we understand from here is that this equilibrium position of this block lies just in the middle of A and B, positions A and B. This is the equilibrium. So, as the block starts from the position A and reaches this equilibrium position of x naught, it will gain a kinetic energy as the net force will be downward. But after crossing through the position x naught, because the block has already gained some velocity, it will not stop here. It will overshoot the equilibrium position and will move down. As soon as it overshoots the equilibrium position and starts moving down, the net force now will reverse its direction, because the spring force will now become greater in magnitude than the force of gravity. The block will start slowing down as it moves from the equilibrium position to the point B, but it is still moving down, right. So, it moves down, but slows down in the process, and by the time it reaches the position B, it loses all of its kinetic energy once again and comes at instantaneous rest. Okay. So, by combining these aspects, now we can understand a lot about the physics of the situation, right. So, energy and force together will help us understand things more effectively, and we shall see that we can in fact use all these applications, the law of conservation of energy, into questions which will be our next topic for discussion, into a particle which is moving in a vertical circle. There is a small bob which is connected with a string of a certain length, and you make it move in a vertical circle vertically, and we want to study its dynamics, what all velocities are there at different points, what is the tension in the string at different points. All those aspects we shall be studying only by using the force equation that we have studied in the previous chapter, Newton's laws, and the energy conservation principles. That will be, we shall see that they are valid there in that situation. So, how we can discuss the details of a situation, we shall see that in the upcoming video.